So in the grade 11 course, you should have become quite proficient using the kinematics equations. And so I'm going to be using them a whole bunch on the board here. And if you're not familiar with them, you should go back and revisit the link on the page for the kinematics equations video, so you can brush up on that before trying to launch into this one. We're going to use projectile motion, so that's throwing a ball or firing a cannonball or anything that flies through the air, and once it leaves the cannon is unpowered. So not like a rocket or a torpedo, but something that you just toss. We're going to use that as an introduction to how things move in 2 dimensions, and to illustrate how once you break something into horizontal and vertical components, you're basically solving the problem this way, ignoring the up and down, and you're solving it this way, ignoring the back and forth. And then those 2 solutions end up coming together to give you the full picture of the motion. So to start then, I'm going to need some grass, and I'm going to need a cannon, and you can always tell a physics teacher because they can draw the most exceptional cannons, like at the drop of a hat. A little fuse and some sparks. Lovely. And so we're going to have this cannon launch something, and it's going to fly like this, and it's going to land and cause much chaos and destruction, of course. And so based on the initial conditions of this cannon, we'd like to know exactly where that is. So how far away is this cannonball going to strike the ground? So I'm going to have to define some initial values. I'm going to set the speed coming out of the cannon at 40 meters per second. So that's the muzzle velocity. And because I can't write and think at the same time, give me a second on that. So that doesn't mean that it's headed this way, 40 meters per second. It doesn't mean it's headed that way, 40 meters per second. It means it's traveling along the barrel of the cannon at 40 meters per second, which is a little bit this way and a little bit up. I'm going to set this angle here, alpha, as 30 degrees. Of course, if you're very advanced, you'll be using radians instead of degrees. But radian measure is not part of this course, and neither is advanced functions a prerequisite for this course. So I don't want to use radians lest we lose some people along the way. So here it is. I have 40 meter per second muzzle velocity and a 30-degree angle pitched up. So the first question we have to ask ourselves is that 40 meters per second tipped upwards at 30 degrees is a little bit forward and a little bit up. And we have to decide how much of each it is. So this thing here has a horizontal piece. We'll call that speed in the x direction. And it has a vertical piece. We'll call that speed in the y direction. Now, since y and x meet each other at a 90-degree corner, I have a right angle set up where I know the length of the hypotenuse and I know the angle the hypotenuse makes with the adjacent side. So this is a trig question from grade 10. So we just need to set up the trig ratios in order to work this out. So how are we going to do that? Well, if I go for the x coordinate, or the x component, I have the adjacent, the hypotenuse, and the angle. Adjacent and hypotenuse is cosine. So the cosine of 30 should be the adjacent side divided by the hypotenuse, which means that the horizontal component of the velocity would be 40 multiplied by cos 30, which is approximately, cosine of 30 should be root 3 over 2. If only I had a calculator that worked. cos 30 is 0.866, which is root 3 over 2, multiplied by 40, gives me 34.64 meters per second. And in the vertical direction, that would be the opposite side and the hypotenuse with the angle. That's a sine ratio. So sine of 30 gives me Vy over 40. Therefore, Vy is 40 sine 30. And sine 30 is 0.5, so Vy would be, let me just confirm that. Sine 30 is 0.5 times 40 gives me 20. All right, so what I've done there is I've divided my muzzle velocity into a forwards component and an upwards component. The instant the cannonball leaves the mouth of that cannon, it is traveling forwards at 34.64 meters per second and upwards at 20 meters per second. So I can write that up here so that I've got that in a more useful place. Got 34.64 to the right and 20 upwards is my initial velocity. All right, good. So I'm going to erase this, and then we're going to sort of look at what all of our initial conditions are and then the final conditions so that we can do some calculations. All right, so the kinematics variables that we have to work with are the initial speed, the final speed, the acceleration, the distance, and the time. So if we start looking at the launch conditions, so what is the ball doing at this place when it leaves the cannon? Well, I'm going to have to note that there are horizontal parts and vertical parts. So those are my x things, those are my y things. My initial speed in x is 34.64. My initial speed in y is 20. If this thing is flying through the air, then it's under the influence of gravity. And if you ask yourself about the components of gravity, gravity accelerates downwards at negative 9.8. So in the vertical direction, I should have an acceleration of negative 9.8. In the horizontal direction, however, gravity doesn't push you forwards and it doesn't pull you backwards. It only pulls you down. So the acceleration as far as horizontal is concerned will be 0. Because gravity is neither speeding you up or slowing you down this way. The rest of these numbers are a bit silly. If I started at the launch point and ended at the launch point, then I've had no opportunity for the acceleration to work. So I have 34.64 and 20. Distance, it has traveled 0 distance in x, 0 distance in y, and 0 time has gone by. All right, so that's how it starts. In order to proceed with this problem, I'm going to have to fill in something that I know later at some other point. And there are two places where we know something. The first one is here, at this place where we'll call it the max height. So at that place, the cannonball was traveling upwards until that spot. It came to stop, and then it started to go back down again. So you've got a final speed in the vertical direction of 0. So I'm going to create another set of columns here for the max height and see what we can fill in. So at max height, horizontally and vertically, So that condition I just identified at max height is that the final speed in the vertical direction is 0. Now you get to write that one in for free. That's always true. It's part of the definition of a max height, right? That thing has stopped rising and has started to fall back down again. I'll be able to fill in these things. The initial speed in x was 34.64. The initial speed in y was 20. Final speed in x at the max height, I don't know because I haven't done any calculations yet. My acceleration remains no push horizontally and a negative 9.8 acceleration vertically. How far has it traveled in x? I don't know. How far has it traveled in y? I don't know. How much time has gone by? I don't know. So I have some question marks to fill in there. I need to calculate this, and I need to calculate this, and this, and this. We'll just leave them there for a minute. The third place where I have some information is this actual target, right, where the cannonball hits the ground. And if you think about that, when it's reached the ground, it has a height of 0. That means its distance in the vertical direction has reached 0. So I'm going to make another column, third set, at the target. We can fill in some information. So I'm going to need to have a horizontal set of numbers and a vertical set of numbers. And the definition of a target is where the distance in the vertical direction has returned to a height of 0. All right. So initial and final speeds, I can still put in 34.64, and I can put in 20. Acceleration is still 0 push horizontally and a negative 9.8 vertically. Vertical distance is 0, but all the rest of this stuff, I don't know how much time it takes, and I don't know how far it has gone horizontally, and I don't know what these final speeds are because I haven't done any calculations yet. Okay. So you notice I didn't ask you a question up here. I just gave you the initial conditions, and we're going to figure out everything we can about this particular projectile motion. So we just have to use our kinematics equations and start working through to fill in some of these blue question marks. Now if you remember from grade 11, the trick to kinematics equations is you need to have 3 numbers. And as soon as you have 3 numbers, you can calculate a fourth using the appropriate equation. So I'm going to look at this column. Horizontally at the max height, I have 2 numbers and 3 question marks. 1, 2, 3. That's not enough information to make any progress. So we're kind of stuck on that column. I look at this column. I have 1, 2, 3 numbers. So that should be enough to allow me to solve both the distance in this position and the time in that position. So I'm going to try and fit that down here. Let's see, I need the equation that connects distance with initial speed, final speed, and acceleration. And if you go back to the notes and you look that one up, it would be VF squared minus VI squared equals twice the acceleration times the distance. So using these numbers, final speed of 0 squared, subtract an initial speed of 20 squared equals 2 times the acceleration, which is negative 9.8, multiplied by the distance. Now I've successfully eliminated all of the letters except for the distance. That's good. 20 squared is 400, negative 400. Be careful about that. The square doesn't eliminate this negative because the negative is outside of the square operator. So just be careful. 2 times negative 9.8 is negative 19.6. So negative 400 divided by negative 19.6 should give me the distance. So the distance is 400 divided by 19.6 gives me 20.41 meters. Now that is rounded, but I think 2 decimal places is good enough for us. So I have just determined that this question mark is 20.41 meters. Which is good. I now know something that I didn't know before. Is it the answer to the question? Well, of course not, because there was no question. But it's something I didn't know about this system when I started. And it is something that was predetermined by these initial conditions. So I'm just going to keep working away until I have numbers every place where a question mark appears on this chart. So finishing off this column, I now have 3 numbers and time. I could try and calculate that one. So the equation that connects initial speed, final speed, acceleration, and time would be Vf subtract Vi equals At. Final speed in the vertical direction at the max height was 0. Subtract the initial speed, which was 20. Acceleration is negative 9.8 t. And I have, again, successfully filled in all the letters except for one. 0 subtract 20 is negative 20. And negative 20 divided by negative 9.8 should give me my time. Let's try that. 20 divided by 9.8 gives you 2.04 seconds. All right, so this question mark here is 2.04 seconds. Now, you notice that I didn't leave a horizontal and a vertical time. If you think about that for a minute, the ball can't arrive at the maximum height position horizontally at a different time that it reaches it vertically, right? The ball has to be one ball. It can't arrive at 2 different places at 2 different times. Because it's not a quantum mechanical object, we haven't gotten to that point yet. Stay tuned until things get weird. So for now, when you're doing these things for normal Newtonian objects, that means things that are big enough for you and I to touch or see or taste or whatever, that you should just be using a single time in both horizontal and vertical. Now, an interesting thing has happened. Because I did all this work on the vertical column, I ended up generating 1, 2, 3 numbers in the horizontal column. So that gives me enough information to calculate these 2 numbers that are still missing. So I'm going to clean this off, and then we're going to finish up this column here. All right, so I have an initial speed, an acceleration, and a time. And I need to calculate a final speed. So the equation that connects VI, VF, A, and T is VF minus VI equals AT. So V final, I don't know. V initial was 34.64. Acceleration is 0. Time is 2.04. All but one of the letters has been filled in, so I just need to solve. 0 times 2.04 is 0. Kick this over, plus 34.64 is VF. So VF is 34.64 meters per second, which happens to match this. And maybe you're feeling a little sheepish at this point, because that's obvious. If there's no acceleration, right? If that means that the speed isn't changing, then the speed at the beginning should match the speed at the end. We didn't know that for certain until we had done the calculations, but I can say it for sure now. And if you want to save a little time, same thing's going to happen here, right? No acceleration in the horizontal direction means that this speed won't have changed at all. So I'm just going to jot that one in and save us some ink. Okay, one more to go in this column, and then we'll know everything about the max height. I just need the position. So the equation that connects time and distance, acceleration and initial speed would be the distance traveled equals initial speed multiplied by time plus 1/2 the acceleration multiplied by the time squared. So distance would be 34.64 multiplied by 2.04 plus 1/2 of the acceleration, which is 0, multiplied by 2.04 squared. It's the time squared. Notice that 1/2 times 0 times this number is gone. So my distance ends up being 34.64 multiplied by 2.04, which is 70.69 meters. So this final question mark in the max height column is 70.69 meters. So what we've just discovered then is that this cannonball, if it has a muzzle velocity of 40 meters per second and it's tipped upwards from the horizontal at 30 degrees, that ball will reach a maximum height of 20.41 meters above the ground. It will achieve that height 70.69 meters from the cannon, and it will happen 2.04 seconds after the ball leaves the cannon's muzzle. So I've just learned everything there is to know about that max height based on the initial conditions. So I'm going to continue this process. I need to finish it for the target. I still have 3 numbers to calculate, so I'm going to erase this and we'll get those done. Alright, so if we were to look at our numbers, I'm not going to use this blue one. I wasn't handed that number in my initial conditions, so I'm going to avoid it. It's also going to do some wonky things like VF squared minus VI squared equals 0, which won't be helpful. So if I dodge these blue numbers for a minute, I don't have enough yellow ones in the horizontal column to do my work, so I'm going to have to work on the vertical first. There's 1, 2, 3 values, so I'm going to get my final speed. Alright, so the equation that connects VI, VF, A, and D would be VF squared minus VI squared equals twice acceleration distance. VF squared, I don't know. VI squared is 20 squared. Acceleration is negative 9.8. And the horizontal distance is 0. 0 times anything is gone. 20 squared is 400. So I have to add 400 to both sides. And to undo this square, I will have to do plus or minus the square root of 400, which is plus or minus 20. Okay, now it's given us 2 answers. Well, that's weird. But if you think about it, the conditions you put in there was an initial speed of 20, an acceleration of 9.8, and a vertical position of 0. Those are exactly the same numbers as you had at the beginning. So what your algebra did is it dutifully returned to you the initial conditions you started with and the conditions at the end. So if I look at this, the plus 20 is here. Right, that's my speed going up. Right, when I finished launching the ball, it was headed upwards. When the ball hits the target, it's not rising anymore; it's falling onto the target. So this number here is the negative option. All right, good. So I need to get my time now. Equation that connects VI, A, D, and T is, let's see, VI, A, and T. The distance is initial speed time plus 1/2 AT squared. So my position here would be 0. Initial speed was 20. t I don't know. It's 1/2. My acceleration is negative 9.8. T squared I don't know. T, half of 9.8 is negative 4.9 t squared. And here's where you have to pull some algebra tricks. I have a t and a t squared in both terms. I'm going to factor that t out. Now if I do that, what I've set up here, right, this has a t and a t squared in it. This is a parabola, and I'll give you a minute to find a bucket and barf in it, because nobody likes parabolas. But this algebra technique, right, of factoring to find the t-intercepts of this parabola that you did back in grade 10 is going to come up quite a bit in this course. So if I factor it, I end up with two cases. This thing times this thing equals 0. Well, that means either case 1, t is 0, right? This thing equals 0, or case 2, this thing equals 0. And if you think about that, when you have two things multiplying each other and the answer is nothing, the only way you can multiply two numbers together and get 0 as an answer is if that one's a 0 or if that one's a 0. It's the only possible options. So you set them up. Case 1 turns out to be your initial conditions, right? This is what you started with. Time is 0. So case 2 then is going to fill in for my target time. So I just have to work that out. Let's see, 0 equals that. Kick this over. 4.9t equals 20. So t is 20 divided by 4.9, which is approximately 4.08 seconds, if you can see it on my very shiny forehead. So that time there is 4.08 seconds. All right, so I'm going to erase this, and then we have one more number to go. That's the horizontal distance at the target. So I'm going to need an equation that connects this time, because I know a time now, time, a distance, an acceleration, and an initial speed. Well, that's this old trooper that we've been using again and again and again. Distance I don't know. Initial speed was 34.64. The time is 4.08 seconds. 1/2. The acceleration is 0. Time is 4.08 seconds. 0 times anything is gone. So my distance ends up being 34.64 multiplied by 4.08, which gives me 141.39 meters. So this number here is 141.39. And if I get this out of the way so that I don't have any calculations lying over the place, you can look at the summary of all the information that we've got here. We started off with some initial conditions, right? That the acceleration was due to gravity, so that's the same all the way across. That the cannon started at the cannon and started on the ground, and the experiment started at the moment we launched the cannon, so that's all set up there. I got my initial speed from breaking my muzzle velocity into components. And then I just track through some things that are true at different places. For example, the final speed at maximum height is 0. And that the vertical position at the target will be 0 again. So starting with these initial conditions and those two facts, we were able to deduce the values of all 5 kinematics variables, both horizontally and vertically, at 3 different positions on the flight path of this cannonball. Now that's pretty remarkable, right? You set the initial conditions and then deduced all behaviors of that cannonball at those 3 particular points. It would be better if we could get the behavior of that cannonball at all points in time, and we're about to in about 64 seconds. But I would like to take a moment to fact check our work here and just to make sure that we have the right answers. So, number 1, a parabola is symmetrical about its vertex, and that's what the max height is. It's the vertex of the parabola that this projectile is following. So if we are doing parabolic projectile motion, then whatever happens in this half has to be mirrored in that half. So if it was 70.69 meters from here to here, it should be another 70.69 meters for the ball to hit the ground. That would be a total of 140, 141.2, 143.8 meters if you doubled this. And that's what we got. So that's encouraging. These 2 numbers are great for fact checking. Now you might be saying to yourself, why don't I just double the horizontal distance in order to get the horizontal distance at the target? Well, you could do that. But you would have no way of checking if your work is correct. If you follow through and use the kinematics variables, you're going to spit out 2 numbers that you arrived at independently that have to be double each other. Now, if that's true about distance, it should be true about time as well. And so if you check that, if it takes 2.04 to get halfway, then it should take twice that to go the other half. 2.04 doubled would be 4.08, which is what we have. You should also have your speed here and your speed here being the same number, but one is up and one is down. And as long as those 3 checks all work out, then you know that you've done your projectile motion problem correctly. So, how are we going to take this information and describe the path of that projectile everywhere? Well, you just need the formula for a parabola. So there were 3 different formats that you had. You had standard form, which had information about the y-intercept in it, which I'm not sure is particularly helpful here. You had factored form, which had information about the x and x-intercepts. And you had vertex form, which used all the information about your max height. I think that's the most useful one. So I'm gonna pop that over here, maybe vertex of a parabola. Vertex form is y equals a, that's the transformation factor, x minus the coordinates, x coordinate of the vertex plus the y coordinate of the vertex. So if I were to try and fill this in, well, I've got my x coordinate of the vertex is 70.69. X minus 70.69 squared, and the y value is 20.4. Alright, I have everything I need except for this a value. Well, if I knew an x and a y location anywhere else on this parabola, I could drop it in there and calculate a. I've got a real easy one. Right at the launch point, x was 0 and y was 0. So I'm going to fill that in. 0 for y, 0 for x. I'm going to kick this over. Zero minus 70.69 is negative 70.69, and 70.69 squared is 4,997. .08. So if I divide this by this, 4997.08, then I have the A value for that parabola. So these initial conditions split to make an initial velocity like that, and I can write the equation of this parabola like so. The Y value is negative 20.41 over 4997.08 multiplied by x minus 70.69 squared plus 20.4. So that's where that ball is everywhere relative to the ground. So if I wanted to know how high the ball was 20 meters from the cannon, I just have to put a 20 here. If I wanted to know where the ball finally reaches a height of 10 meters, well, I just put a 10 there, solve for x. And we'll do that in a minute. I want to do the same thing, but instead of coordinated for position on the ground, I'd like to do it for time, right? So how many seconds later is it up at a certain height? So I'm going to start with this again, but instead of using x, I'm going to use time. So height is a function of time instead of height is a function of x. Well, the mechanics of this aren't any different. I've got an A value, I have t, the t component at the vertex, right? The time at the max height is 2.04. And the height is 20.41. So to get that A value, I just need to use another point on the parabola that I know about. And so at launch, the height is 0 and the time is 0. So I can get away with that again. I'm going to kick this over to the other side. Zero minus 2.04 is negative 2.04, and 2.04 squared is 4.1616. So the A value would be negative 20.41 divided by 4.1616. So if I record that as a parabola coordinated for time instead of position, I'd end up with negative 20.41 over 4.1616 t minus 2.04 plus 20.41. Now this fraction down here, 20 divided by 4 is about 5. Be a little less than 5 because this thing is a little bit bigger than 4. And I bet if you popped her into your calculator, you'd find that it was negative 4.9. That's not a mistake or an accident or coincidence. But I'll leave that for you to ponder, see if you can figure out why. So I've taken these initial conditions, made components for velocities, and then made a model that tells me exactly where that ball is at any point in x or at any point in time. So I'm going to erase this stuff. I'm going to try and use these models to do something inquisitive. So there's no point in having cannons if you're not trying to shoot cannonballs into your neighbor's lawn. So perhaps your particularly industrious neighbor has built themselves a 10-meter high wall, and you've been able to wheel your cannon to within 85 meters of their 10-meter wall. And I'd like to know if these initial conditions will cause the ball to slam into the wall or to clear the wall and land in their backyard. Well, I have a model that tells me how high that ball is for any position in X. And I've been given a position in X. So all I need to do is put 85 into this parabola, and I should be able to calculate the height. So let's give that a try. Y equals negative 20.41 over 4997.08 multiplied by 85 subtract 70.69 squared plus 20.41. Okay, well, this is just an exercise in bedmas, so negative 20.41 over 4997.08. 85 minus 70.69. Nope. 85. Nope. 85. Subtract 70.69. Gives me 14.31. 14.31 squared is 204.7761. All right, so that number multiplied by negative 20.41 gives me negative 4,179 divided by 4997.08 gives me negative 0.836 plus 20.41 gives me 19.57 meters. All right. So, what's the answer to the question? Will the ball clear a 10-meter wall located 85 meters from the cannon? Well, yes, because the cannonball is almost 20 meters up in the air at that point. Perhaps you can see why cannons are so effective. 10-meter wall, that's 30 feet high. That's like a 3-story building, which is a heck of a wall. So if you were to try and build a 20-meter wall to stop your crazy neighbor from firing cannonballs at you, that's like a 6-story building. That's a lot. So once you've used your initial conditions to create this parabola, I mean, we could change this to anything. We could do a 20-meter wall located 90 meters from the cannon. I can change any of those numbers. I could also figure out, let's see, let's flip this question around. How far from the cannon, or how far from that wall, from the 10-meter wall, must the cannon be to just clear it? Can be to launch projectiles over the wall. How far from the 10-meter wall must the cannon be to launch projectiles over it? There we go. Question mark. So if I get rid of this here, maybe a bit premature, I'm still using this model. The only thing that's happened is instead of having a number for x, I have a number for y now. So in it goes 10 equals negative 20.41 over 4997.08 x minus 70.69 plus 20.41. So I'm going to bring that over. 10 subtract 20.41 would be negative 10.41. X minus 70.69 squared. So I'm going to take my 10.41 I'm going to multiply by 4,997 times 4,997.08, which gives me 52,019 divided by 20.41, and I get 2,548.73. Alright, now it's important, these negatives were critical so that I ended up with a positive here, because I'm going to have to square root in the next line, and I can't square root a negative number. So in fact, if that had happened to you, right, like if I'd made this, well, in order for this to end up positive, this would have had to be bigger than 20, well, like 21. So we've already decided the max height was only 20.4 meters. So if I asked you when a thing with a max height of 20 meters passes over a 25-meter wall, well, obviously that doesn't work, and the algebra would be confirming it for you by spitting out a negative. Fortunately, we have a positive here, so we can continue to square root both sides. Square root of 2548.73 is plus or minus 50.485. Kick the 70.69 over to the other side. Instead of negative, it will be positive. So x is either 70.69 subtract 50.485. It's 20.205 meters. Or 70.69 plus 50.485. 121.175 meters. So why two answers? Well, if you got your cannon within 20 meters of your crazy neighbor's 10-meter wall, that ball will get over the wall on the upstroke, right? It'll be headed upwards, and it will be high enough to get over the wall. If you put your cannon 121 meters away from your crazy neighbor's 10-meter wall, then that ball will rise, crest, and still be sufficiently high on the way down when it goes over the wall to be able to get it done. So as long as your cannon is within these distances of the wall, then you're going to be able to get a ball over top of it without slamming into the blocks. So the last question we have to answer is one about time. So I'm just going to do one of these instead of two. I'll erase this first. So I have a height, and I've been asked about time. Well, that's this model here. So 15 goes in for y. 15 equals negative 20.41 over 4.1616 time minus 2.04 squared plus 20.41. I'm going to kick this over. 15 subtract 20.41 would be negative 5.41. Make sure that's right. Okay. I'm just going to check this. 20.41 divided by 4.1616 is 4.9 as advertised. I wonder why that happened. Time minus 2.04 squared. 5.41 divided by 4.9. Notice they are both negative, giving you a positive value of 1.104 on this side. Square root both sides. 1.05. 1.057, I suppose we can keep that. Plus or minus. You can kick the 2.04 over there. 2.04 plus or minus 1.057 equals my time. So my time is 2.04. Subtract that number is 0.989 seconds, or time equals 2.04 plus 1.057 is 3.097. Right. So if the question is phrased that way, during what window of time is the ball more than 15 meters in the air, then the ball is more than 15 meters in the air between 0.989 seconds into flight and 3.097 seconds into flight. If the question had asked you how long is the ball more than 15 meters in the air, well, that's when it stops being that high. This is when it starts. So the answer would be the difference between the two. So 3.097 minus 0.989 is 2.108 seconds. So this minus this gives you this. So how long is the ball more than 15 meters in the air? 2.108 seconds of the flight time. So there is a question on the practice problems about, I think it's about a sniper rifle, which is kind of fun. So you're going to have to take your initial speed and your angle of inclination, split it into components, use those components and the big chart in order to solve all 5 kinematics variables, both horizontally and vertically, at the target, the max height, and the launch point. Once you have all the information, you should be able to write a spatial version of the parabola. You should be able to write a temporal version of the parabola, and then answer a few questions about it. Good luck.